Hello everyone, guys. Hope you all are doing well. Welcome once again. Welcome back to Shaurav's classes. So today we are back with our session, Tomato Problem Solving Objective. We will solve objective problems here. Those who are new to this particular session of videos, let me introduce that to them that this video or this set of videos is basically intended for ISI aspirants. Aspirants for I.S.I. here stands for Indian Statistical Institute. So Indian Statistical Institute is one of the most premier institutes in India for mathematics, statistics, computer science and other subjects. So today we will solve problems from Tomato. Tomato is the abbreviated form of the book Test of Mathematics at 10+2 level, which is published by I.S.I. themselves. I.S.I. professors expect that a person appearing for the entrance should be thorough with the problems of the Tomato so that they could easily clear the examination with some of their efforts. So we are back with problem solving session for the objective part, and the question for today is as written on the board: the number of functions f of 4 to 4 such that fx less than equals to 2x is option A 32, option B 64, option C 128 and option D 256. So here 4 means is defined to be the set of 1, 2, 3, 4. Okay, so this question basically asks you to find the number of functions f of 1, 2, 3, 4 to 1, 2, 3, 4 such that fx less than equals to 2x. So the question asks you to find the number of functions and pick the correct option. The options here are 32, 64, 128 and 256. So I give you some stipulated amount of time to come to the answer, and after that I will solve the problem. Okay, so the stipulated time that was meant for this question is over. So I provided less time in this question. This is because this question is not difficult as it seems. So if many of you, I guess, have solved this question, but those who haven't solved, there is nothing to be disheartened. I'll just give you some simple strategies so that you can solve problems of such kinds. So for solving questions on functions, it's very important to make the arrow diagrams. So arrow diagrams are very important part of visualization of functions. So suppose you have a function from a set A to set B. So I always recommend you that during problem solving, just draw these diagrams. So this is the arrow diagram representation. So A, B, and if any element of A, say this element of A is related to some other element of B, then just give an indicating arrow. So this helps in visualization of the function, and humans in general have a tendency to visualize, to see things or visualize things more than just keeping on with the lengthy writings. So I recommend you always to draw such arrow diagrams while solving problems like these on mappings and functions. So I'll just use this diagram to explain you. So according to the question, our set was the set that was given, that is, so I'll just rub it off the arrow part, as this was only for the example part. So the set in the question that was given was 1 2 3 4 to 1 2 3 4, and the rule was fx less than equals to 2x. Okay, now observe that fx less than equals to 2x applies. So what is the twice of 2? So the twice of 2 is 4, which is present here, and fx less than equals to 2x, so f of 2 can be 4. F of 3 is 6, 6 is not present here, so we don't have a problem. So what makes the problem? The problem is with 1. We see that f of 1, I'm just writing down in the middle, must be less than equals to 2, that is, which is equals to 1 or 2. So f of 1 can be 1 or 2. Okay, so 1 can be mapped to 1 or 2. So there are only two possible types of maps. Okay, and we are mapping 1 with some other thing. So we know in combinatorics or in permutation combinations, the fact that we utilize is the AND part, where A and B, the number of ways work A can be done and work B can be done is A into B. So the number of ways in which 1 can be placed is 1 or 2, and the number of ways in any others can be placed is 4 number of ways. So every other can be mapped into 1 of 1 2 3 4. So every other can be mapped, of course they can be mapped into 1 of 1 2 3 4, because say suppose if 2, so 2 can be mapped to 1, 2 can be mapped to 2. This is because all satisfies this equation. Okay, so what we observe is that these three elements can be mapped into any of 4 numbers. So these three elements can be mapped into any of 4 numbers, but 1 can be mapped only in 2 numbers, 1 or 2. So since this can be mapped, so 2 can be mapped in 4 ways. This is because there are 4 numbers present. 3 can be mapped in 4 ways, again because there are 4 numbers are present. 4 can be mapped in 4 ways because 4 numbers are present. But 1 can be mapped in 2 ways only. So this was the thrust in the question, that 1 can be mapped in 2 ways only. So 4 times 4 times 4 equals to 2 into 2. So 4 cube becomes 64. 64 to the 128 is the answer, which according to the question that I wrote on the board is option C. So this is the solution of the problem. So regarding the general commentaries of the problem, I would say that this was a purely simple problem of combinatorics and map counting, in which you just need to recognize what maps to what. So combinatorics forms, as I said, a very important topic. So this was just an example of the combinatorial problem that I.S.I could give, and this is fairly easy. So this is not that tough. So I expected you all to do it by yourself. And as I said, that the most important part of the question, so how did I make the visualization clear? I make the visualization clear by drawing these diagrams, arrow diagrams. So I recommend you, so when you are solving problems related to permutations or related to mappings or related to functions, I always recommend you to draw arrow diagrams so that you can just have a better look at the problem, a better outlook to the problem, and this will enhance your problem solving speed. So this was the first problem for today. So let me, without further ado, let me get to the second problem. So the second problem says that the number of onto maps So this is the second problem for the day. It says that find the number of onto maps such that the sets are given. This is A1 to A7 and that is B1 to B3, such that exactly 3 elements map to B1 is. So this says that exactly 3. So 3 must map to B1. Option A is 490, option B is 558, option C is 560, option D is 1680. So this is the problem that I chose. This is because finding number of onto functions and into functions are one of the major problems that arises within the common problems that arises within the topics students of mathematics, and this problem along with finding the number of onto functions has a slight tinge that 3 elements map to B1. So I recommend you or request you all to try this question and I'll get back to the solution. Okay, so the stipulated time that was meant for this question is over. So if anyone could have solved it, then it's very good. And if you have cannot solve it, that's also fine. Don't be disheartened. This is because after I give you this concept, you will be clear in how to solve problems of this type. This is because these types of problems frequently come in I.S.I and are hot favorite for the I.S.I professors. So they attempt to give these types of problems every year, more or less. So I'll show you one example and I'll give you the concept, and after that you can solve it. So I have given the concept of onto functions already in previous parts, and I have told about the principle of inclusion and exclusion that is used to find the number of onto functions. But here the problem is a bit separate. So as I have always told and recommended you that please draw the arrow diagrams before solving any mapping problems or functional problems like this. So this is set A and this is set B. So I took the set B smaller. This is because the cardinality of set B is less than that of set A. So set B has B1, B2, B3 elements. So these are the elements, and A1, A2, A3, A4, A5. I need to make the set a bit longer. Say A5, A6 and A7. So this becomes my set of A, and I need to define a function from this set to this set. So what it is told, it says that exactly 3 elements must map to B1. Now, of course, you see that in the B set, B1 is not a problem. This is because by our condition of surjectivity, or the condition of being an onto function, B1 has 3 pre-images. So the onto function's condition says that B1 must have at least 1 pre-image. So it has 3 pre-images, so that is not a problem. And The 3 elements also is not a problem. So what can I do? So from these 7 elements, I can choose any 3 to go to B1. So choose, I'm just mentioning the steps so that the thing becomes easier to you. Choose any 3 and send to B1. So since B1 has exactly 3 elements, I have chosen exactly 3 elements in 7C3 ways. I hope that the other part of the board is already clear. So let me write it in the middle. So in 7C3 ways, I have chosen and send to B1. So this is the first step of my problem. Choose any 3 and send to B1. So if I choose these 3 and this one, if I eliminate, so what do I have now? So these 3 elements are already mapped. So the A1, A2, A3 or any of the 3 elements that are mapped are now of my concern. So I can just delete them. So if I delete them, what is my set? My set is just A4, A5, A6, A7 and B1, B2, B3. This is because, of course, and B1 is deleted. So B2, B3. So these are my final sets. So why these are my final sets? This is because you see that exactly 3 elements has already mapped to B1. So if any of other elements is mapping to B1, then it becomes 4 elements and therefore a contradiction arises. So we cannot include B1 again. And what is the logic for rubbing A1, A2, A3 or any 3 elements that are mapped to B1? This is because exactly 3 elements are already mapped to B1, and by the definition of existence of a function, that element cannot be mapped, I repeat, that element cannot be mapped into any other elements of B. So what we are left is 4 and 2, and 4 elements and 2 elements in B, and the question has just reduced to the simple question that I need to find a surjective function from a set of 4 elements to a set of 2 elements, and from the principle of inclusion and exclusion I can say that the trick that I usually use for principal and exclusion is include what is needed. So I have include the number of functions that is needed and exclude what is not needed. There are 2 cases in which these 2 might have been left alone. So 2 cases. So there are 2 elements or 2 cases. So that's what I usually do in the principal and exclusion. So this is again the part. So include what is needed, exclude what is needed, and the exclusion is excluded. And therefore the answer is just the multiplication. This is because the AND logic is working here again. How to do map 3 and the surjectivity. So just this works, and the result finally is 35. So 7C3 is 35 times 2 power 4 is 16, and 16 times 16 minus 2 is 14. So 35 times 14, and by simple computation you can get it is 490. And from the test of mathematics book that I have with me, so this is the test of mathematics book that I am talking of, and we are doing questions. And so from the test of mathematics book I have with me, this is the book, so I just see that which option is 490. So 490 is present in option A. So option A is the answer. So here, as I said, that in this question and from the book test of mathematics, in this question the main part is to find the number of surjective functions, and the main thrust here, there was no specific thrust. This question was also quite straightforward, typical mapping type problem, a typical functional based problem. And as I said that in functional based problem it's always better to use an approach through arrow diagrams, and onto functions is a very simple concept, as I have told you, is includes the principle of inclusion and exclusion. I can just use that, and so we could easily conclude with the second problem. So I hope that you have learned this tip and trick. So, and I hope also that you will follow this in your exam hall, as this will increase your efficiency in solving problems. So that's why these tricks are being discussed. So these tricks are being discussed only so that you can just improve your efficiency in problem solving with little effort, so that you just use these tricks in the exam time, and you will see that how magically or how thrustically this trick works. So now I'll get to another map counting problem to expose you to a wide variety of examples from the book Test of Mathematics. So another map counting problem I'll give just to demonstrate. So this is a bit tougher problem that I'm coming to. So but this tough problem will help you to increase the conceptual part of the subject matter that you will be going through. So the question is, so the number of maps f from 4 to 4, so as I have said that this notation means the set of 1, 2, 3, 4, such that f of x is 1, 6, 9 and 10. So I recommend you to try this problem for a few moments and I'll get back to the solution. Okay, so the stipulated time that was meant for this problem is over. So I hope you all have tried it, and not being able to do this is very natural. This is because this is a bit tough than the previous ones. So the concept is as same as the previous ones that I am going to use, and the main important thing is trying. So you all have tried. So if you have really tried, being truthful to yourselves, so I hope that you will easily get the solution that I am going to give, provided that you have tried it in the time that I give. So as I said that the function is from 4 to 4, and arrow diagrams is again our only key to solve such kinds of problems, as I have already told. So here I will draw 3 boxes. This is because why I am drawing 3 sets. This is because I am drawing 3 sets A, B, C. So A1, A2. So let me name as A1, A2. Because the problem given is f of x. First time fx gives a value and then I again operate f. So this rule from a to a is f and this rule from a1 to a2 is again f. 1, 2, 3, 4 elements. 1, 2, 3, 4 elements. 1, 2, 3, 4 elements. Okay. So a to a1 is a set, a to a2 is another set, and a to a3 is the thing. So here that I'll teach you a very important trick which I used to remember. So this is a very popular trick that is used for map countings like this, that is known as the bootstring method. So remember the name, because remembering the name sometimes makes you remember the process of the method. So this process that I am trying to teach you for this problem is the bootstring method, and bootstring is a very important method in counting problems like these, when you have especially functions that are double mapped or triple mapped or multi-mapped functions. So this is basically the bootstring method. So why it is the bootstring method? So you will easily know that why the name of the method is bootstring method after we go to the solution part. So we partition the time in the two classes. The un is un minus 1 plus n minus 1 un minus 2. So we need to define what un and un minus 1 is. So I hope that this is not very clear. So these types of relations, as I have also previously told, that these are called recurrence relation, and I use these recurrence relations to solve the problems. So you see that suppose you have a shoe kept in front of you, or a boot. Now these boots have laces, isn't it? So just imagine that you have a boot like this, and what you do to tie the lace? For tying the lace, you first give a simple knot. Now what you need to do for that knot? You first cross those and then enter one of those into the hole that is made by the cross. So for that knot that you tie, what you need to do is you need to make a cross like this and enter this cross through this hole. It means that this is just like getting back to the point from where you have started, isn't it? So what we do usually in boots, in tying the laces of the boots, we usually do is we first make a knot like this. So if I had to, okay, so I have a thing to demonstrate. So let this be, so imagine this to be the boot lace. So what I do is first we do make a knot like this, or this garden is not at all a very good representation. So let me see. So this can be a very good thing. So just imagine this string. So the string that I am holding, or the string that I am showing. So imagine this string to be the strap of your boot. So what we do is first, if my hand is the shoe, first we make a crisscross, and then just imagine this step. So this step we make it inside, and that gives me a knot. So let's try that again. So this is the lace. I am just crisscrossing it as it's shown, and I just tie it down. Okay. Now in this problem, I will not use this lace technique, or I will not tie the laces properly, but you can see that in this problem the concept I use is similar to just like this. So I will demonstrate it. So just imagine that this digraph is map will look like a shoestring. So we partition the tying in the two classes. So we need to tie the string, and we have the classes. So these are the A1, A2 are the classes. So just like boot has two classes like this, the boot has two classes, and so A1, A2, so we just divide it into two classes so that we can get back. So the classes are the whole one tied horizontally and obliquely, fixed point or exchange points. So this basically means that suppose this is a point, so you can see that both the knots that I have told lies in this point. So this point is the fixed point, right? Because the middle point of the shoe doesn't, when you tie the knot, it always comes. So this point where the knot is tied, or where the knot is withheld, is the middle point of the boot. So what we do is A1 is the middle point of my boot, where we just tie these laces of A and A2 to solve this problem. So what I do is we partition the two underlying classes to whole 1 and whole 2. And what we do is we just write UN means the number of functions or number of maps for n number. So I am generalizing it to n parts so that you can just use it. So the number of UN functions is just, you can write it as UN minus 1 plus n minus 1 into UN minus 2, where UN is the number of such functions with n elements. So UN is the number of such functions with n elements. So number of such functions with n elements. So what did I do? So let us suppose that the number of such functions with n elements be UN. Okay? Then the number of such functions with n minus 1 element will be UN minus 1. Now notice that the number of such functions with elements n minus 2 will again be UN minus 2 following the similar rule. So what am I basically doing is just UN equals to, so I have UN minus 1, so let's consider that once f has n elements and I want to find the number of maps. Now what if the number of maps, if f has n minus 1 elements? So if n have n minus 1 elements, can I just devise a method so that I can approach from n minus 1th element to the nth element? Of course I can. This is because if I map all the n minus 1 in UN minus 1 ways, as the UN is the number of functions, then after n minus 1, so why did I multiply n minus 1? This is because in the next case all the n minus 1 elements needs to be mapped. And in how many ways the n minus 1 elements can be mapped? In UN minus 2 ways. So I hope that I am not very clear, so let me just repeat it. UN is the number of such functions we get with n elements. UN minus 1 is the number of such functions with n minus 1 elements, and UN is the number of such functions with n minus 2 elements. So I have done with this generalized approach so that you can solve with any cardinality. So here the problem in the question was 4, but you need to have the concept of solving with any n. So any might be given, it might be 100, 101, 102, you might be able to solve. So for that I have taken n elements, so UN is UN minus 1, so how does it come? So UN, so the number of sets with n elements. So imagine the function with n minus 1 elements is mapped in such a way such that f of x equals to x, and the number of such ways is UN minus 1. Very good. Now when the nth element come, now what is the problem with the nth element? So when the nth element come, in that case what happens is, suppose the nth element has to be mapped, so the nth element here has to be mapped with sum of A1 such that they get back to A2. Now some element of A1, since the function is given, so some element of A1 must have to be related to some element of A2, and that was the concern, and that was what I have assumed in UN minus 1 that had happened. But for that case we need to decrease one element because that element is already mapped with some other element which is not in U1. I hope I am just repeating this fact again, that in the Bootstring method what we are trying to do is we are trying to find a fixed point. So how many fixed points will be there? So as I showed you the knot, so the knot must contain a fixed point. UN minus 1 plus n minus 1 times UN minus 2. This is because after adding the n elements in the previous, there were n minus 1 elements, and mapping those n minus 1 elements was the same as mapping n minus 2 elements from F to identity maps. This is known as the Bootstring idea. So I hope that you have understood it. So if you have not understood, I have given a 3 times repetition. Just rewind the video to check it. So this is the general expression. I don't recommend you, and I never encourage you to remember this expression. I always encourage you to derive such expressions in the hall, but I always will recommend you to remember this method known as the Bootstring method. This is because this is really a very clean sheet or approach to solving problems like this. Means you can get perfect solutions and it will save much more time. So un minus 1, n minus 1, un minus 2. So what is u1 here? So what does u1 represent? That's the number of functions with one element to one element such that f of x equals to x. So number of functions with one element to one element is always f of x equals to x, and the number of functions is always 1. So u1 equals to 1. And u2, by similar logic, u2 must be 2. Why? Suppose you have forget these. So why u2 equals to 2? Let me explain. So let me have a clear-cut explanation once again. Okay, so here is the raster. So suppose I have n elements. So I am getting into the bootstrap method again once more so that things become very clear to you. So suppose this has n elements. So please understand this method very properly. This is because one of the important methods. So what we are discussing is the bootstrap method or the bootstring method. So what I am doing is basically, so say I have a mapping of un minus, so un be the number of such mappings, un is number of such functions with n elements, un minus 1 be the number of such functions with n minus 1 elements, and un minus 2 is with n minus 2 elements. Okay. So what I do basically here is that, suppose I want to map, so the mapping can be, so f of 1 must be 1. So in how many ways f of 1 can be 1? You can see that 1 goes to 1 and that goes to 1, of course. 1 goes to 2 and 2 maps to 1. 1 goes to 3, 3 maps to 1. 1 goes to 4, 4 maps to 1. 1 goes to n minus 1 and that further maps to 1, and 1 goes to n and that maps to 1. So this is a possible case, and considering all these possible cases, I have un to be the number of all possible functions that happened. Now let's get that, suppose I rub off this n from the beneath. So the n is rubbed off from beneath. Now I have n minus 1 element. So how many ways to map n minus 1 elements? That is un minus 1 plus. Now when the nth element comes, so when n minus 1 element, when the nth element comes here, everywhere, now these n minus 1 elements are mapped in whatever order and in all possible orders they can. But now the n element has come and n must be mapped such that f of n equals to n. So one of these maps might have lead to n minus 1, but there are no maps that might have lead to n. So there are only one map that can lead to n, and what can be that map? N to n to n. Or might not be the case. So this is one case, that n to n to n is one case. Or might be that this n can be mapped to something else, just I change the configuration a bit. So if I map this element to some other element, then 1 from n minus 1 has to map to n. This is because that was the terms of the function. So 1 of the n minus 1 must be mapped to n. So if 1 of n minus 1 must be mapped to n, so what I do is I remove the last two elements. I remove the last two elements, and now what I have is n minus 2 elements in each set. Now when I mapped one of those n minus 1 elements to n minus 2 elements, so I need to find the mapping of n minus 2 elements. But I have already found the mapping of n minus 2 elements, and that is un minus 2. And so this is the bootstrap expression as I have told. Okay? So u1 equals to 1, that is the number of functions with one element equals to 1. This is because you just forget everything and cover it up like this. So this is my duster. So cover it up like this, and you see that there is only one element, and 1 goes to 1 goes to 1 is the only possible choice. Now, if you have, suppose you have two elements, then what are the possible choices? So just ignore the rest of others. So you just have two elements. So what are the possible choices? 1 goes to 1 goes to 1, 1 goes to 1 goes to 2, 2 goes to 2 goes to 2, 2 goes to 2 goes to 1. So there are two choices. Going to 1 there is two choices, going to 2 there is two choices. So as a whole there are two choices. Now how we will calculate u3 and u4? Because the function here asks for the value of u4. And from this step what I can do is I can find the value of u4 from this expression, the expression that I have marked in bracket. So just let me rub the upper part. So let me just rub the upper part, and I have u1 equals to 1, u2 equals to 2, and therefore u3 equals, we get u2 plus 2u1. So what does that become? So 2 plus 2 into 1 is 3, and u4 is 3 plus 2 into u2, that is 2, so 4 plus 3 is 7. Oh, sorry. So wait a minute. Oh, sorry. I have written, this is a very unintentional mistake. So that is 4. And if that is 4, then 4 plus 2 times. So 4 minus 1 is 3 times. Sorry, I did a calculation mistake here. So please don't mind for this mistake. I highly apologize to you for this unintentional calculation mistakes. So 4 plus 6, that is 10. So the number of function is 10, that is the answer. And according to this tomato book of ISI, so let me just find that which is the correct option. So the correct option here stands to be option D. So this is the correct option. So I just recommend you to pause this video and watch this thing again. Now what I say is that today we have encountered many problems, including, and we have learned quite a lot of concepts. So the two concepts that we learned today was principle of inclusion exclusion, arrow diagram, and the bootstrap method. So the bootstrap method is a very important method. I recommend you that please don't stop at this video. This video is only for your guideline. What you need to do to enhance your problem solving experience or to enhance your problem solving speed is to practice these tricks again and again from the test of mathematics book. You will get a bunch of problems from the test of mathematics book, and if you are seriously preparing for ISI CMI, you need to solve test of mathematics book and Saurav sir's classes study materials. Saurav sir's classes provides rich quality study materials which includes all of these tricks explained in words, and you will find a bunch of related problems that are there in the materials, and those will help you to enhance these tricks. So those will help you to enhance your ability to solve problems using these tricks. And you need to practice, because when practice makes a man perfect. If you don't practice, then you won't be able to incorporate such tricks in the exam. So best wishes to all of you for the exam. Hope you clear it. Stay tuned with the next video, and thank you and goodbye.